Welcome dear viewers in this video lecture, and today our topic is data representation. So far in previous videos we have seen only positive number, that is we are able to represent a positive number in number system with different bases. But numbers can be also negative, and how we can represent such numbers is the next thing we need to understand. Before discussing how to represent negative numbers, we need to understand why we require representation of negative numbers as well. For this, consider the following four basic arithmetic operation: addition a plus b, subtraction a minus b, multiplication a multiplied by b, and division a divided by b. You can see that subtraction can be written as a plus minus b. That is, subtraction is in fact the addition of a positive number and negative number. Therefore, if we have the representation of positive number and a negative number, we can say that subtraction is equal to the addition. Similarly, we can also see that multiplication is some sort of repeated addition, and your division is repeated subtraction. But I already told you that subtraction is some form of addition of positive and negative number. Therefore, I may write this, that division is also some sort of repeated addition. What we can conclude from this is that if we have a hardware resource that is capable of doing addition operation, we can also use same hardware resource for doing other operations such as subtraction, multiplication, and division, provided we are able to represent negative numbers in proper form. Before we proceed further, let me first formally discuss what are the various data representation methods. So we have broadly two data representation methods. One is magnitude and another is complement representation. In magnitude, we have two other types, that is called unsigned magnitude representation, and another is called signed magnitude representation. And similarly, in complement form of representation, we have R's complement and R minus 1's complement, where R is the base of the corresponding number system. In magnitude unsigned representation, we can represent only positive numbers, and this is something we have already done. In all other data representation methods, we can represent both positive and negative number, but it must be noted that complement method, that is R's complement and R minus 1's complement, are fundamentally used to represent negative numbers. Now let us discuss magnitude signed representation of numbers. In magnitude signed representation of number, positive number is represented by appending 0 before the most significant digit or most significant bit of the number. And negative number is represented as by appending R minus 1 in front of MSD or most significant bit. Now what is this R? Again, I must reiterate that this is the base. Therefore, a signed number n in the base R can be represented using magnitude signed representation as follows. Here in the subscript, you can see that SM means signed magnitude form, and this S is the sign digit, and this is equal to 0 if the number is positive, and this is equal to R minus 1 if the number is negative. To understand the concept, consider the following example in which we have a number 1, 3 in different bases, and we have to represent this number in the signed magnitude form. So let us start with plus minus 13 in the decimal base. So plus minus 13 in the decimal base has to be written in the signed magnitude form. So let us write first plus 13 and minus 13 in base 10. So plus 13 is to be written by appending a 0 sign in front of the MSB, that is 0, 1, 3 is the signed magnitude representation of plus 13. And for negative, we have to append R minus 1. So R here is 10. So the signed magnitude representation of minus 13 is 913 in the base 10. Likewise, we can represent plus minus 13 in base 8 as plus 13 as 013 in the signed magnitude form, and minus 13 as 713 in the signed magnitude form when the base is equal to 8. Similarly, we can represent 13 in the base 13 in the base 16. So plus 13 plus 13 in the base 16 can be represented as 013 in the signed magnitude form, and minus 13 can be represented as 16 minus 1, that is 15, and 15 is represented as F13 in the signed magnitude form. Similarly, this binary number can be represented as plus 1101 can be represented as 01101, and minus 1101 can be represented as 2 minus 1 because base is 2, that is 1101 in the signed magnitude form. Now the question arises, as we have represented positive and the negative number, if this representation is really compatible with the arithmetics. To check whether arithmetic works in the sign and magnitude form, let us do the subtraction as follows. 13 in base 10 minus 13 in base 10 will be equal to 0. 13 in base 8 minus 13 in base 8 is equal to 0. And 1101 minus 1101 in base 2 will be equal to again 0000, which is equal to 0. But if we do this subtraction in the sign and magnitude form, then what we will get is that it will be 013 minus 913, but we do not have to really subtract them, we have to add them, because minus 13 has been represented as 913, and we need to just add these two numbers. So what we will get is 926, which is not equal to 0. Similarly, here we will get 013 plus 713, which is equal to 726, which is again not equal to 0. Similarly, in the binary form, we will get 01101, that is to be added with 11101, which is now equal to 010101, and again this is not equal to 0. So result in each subtraction process should have been 0, because this is the representation that we wanted to do for the negative numbers. So but the thing is, this is completely against to the arithmetic rules. What I mean to say is that we have proposed sign and magnitude representation to convert subtraction into addition, but the results are quite contrary, and it means that this representation does not have worked for us. But the question again is that why we are discussing this. And in the digital textbooks, you will see that this is the first thing that they use to represent the negative numbers. The answer to this question will get clear in the upcoming lectures. This is all for now. Thank you.